Good day, everyone. My name is Peng Luo. I'm the R&D Technical Advisor at the Saskatchewan Research Council. It's my great pleasure to give this presentation on CO2 EOR and the storage potential in Saskatchewan at the 2021 Williston Basin Petroleum Conference. So this is a really big topic that it's impossible to cover all the information in 25 or 30 minutes. So I will be giving a highlight review of the status of the art at Saskatchewan's current situation, and also the laboratory evaluation strategies for CO2 EOR and the storage. So when we talk about the CO2 EOR and the storage, in recent years, in particularly, these two terminologies are connected to each other most of the time, while in the past, CO2 EOR has been discussed a lot. Technically, they can be different or similar or the same, depending on how the CO2 is stored or where the CO2 is stored. So if you're talking about the CO2 EOR, which means CO2 is stored at a depleted oil or gas reservoirs. For the heavy oil reservoirs, then CO2 injection can be immiscible conditions, and the main mechanism would be viscous reduction. But if we are talking about CO2 storage or flooding, in this case, into medium or light oil reservoirs, that most likely will be miscible or near miscible conditions. While we're talking about CO2 storage in geological formations, the most often ones we're still talking about the depleted gas and oil reservoir. So in this way, they are the same concept. But more and more popular options recent years are the CO2 storage in saline aquifers, which we'll be discussing the Aquistore project, one of the most famous ones in a moment. And then options include others geological formations such as salt caverns, coal-bed basins, and the deep seas. Geographically, Saskatchewan has so-called 4 areas for the oil pools distribution. So each pool has different oil properties, distributions, also as well the different recovery methods. So in a more detailed way that we'll be discussing in a moment, we'll talk about the different oil properties and the different reservoir properties and how this will affect the CO2 sequestration or EOR. Then talking about the saline aquifers in Saskatchewan, some research have been done over the years and that identified a number of possible saline aquifers. And the one that has been implemented in the field is, of course, the deadwood formation, the Cambrian age deadwood, which is down to the southeast Saskatchewan, about 3,300 meters deep. When we say CO2 storage in saline aquifer screening, the most important factors are the tectonic stability of the formation. So you want to have the formation usually as deep as possible so that it's stable enough or high pressure enough so that the CO2 won't have the leakage concerns for, say, next 1,000 or millions of years even. Then also we need to discuss the storage capacity of the aquifers. It should be sufficiently big so that we can store enough amount of CO2 in an economical way. And the major CO2 emitters in Saskatchewan, here we list 10 of them, the biggest ones. Of course, you can see the majority of them are from the power station from Saskatchewan. And the biggest one here at the Boundary Dam Power Station, followed by the Shand, the Popper River Power Station, and also we have several big ones in the Lloydminster area. While we play with this image that we overlaid oil pools distributed in Saskatchewan, then we can have some rough idea how easily or how important that the vicinity of the CO2 source, the big number or the transportation factors will kick in so that, when you do the CO2 storage or CO2 EOR for the depleted oil reservoirs, you will find where there's enough CO2 source around. So let's look at some details of the oil pools in Saskatchewan. As we know that the 4 areas have some different oil properties. So in area 1, mostly in the Lloydminster area, that we see the heavy oils reservoirs in the Mannville age. When you look at the API gravity, they are mostly between the 10 and the 16s, so the close to the bitumen, and therefore the most important recovery mechanism for those heavy oils are thermal or the cold oil production. Come to the area 2 in the Kindersley and the Kerrobert areas, there we actually see 2 different types of oil. One is the Bakken heavy oil in this case, and the other one is a Viking, Cretaceous Albian age Viking oil with a very high oil quality of higher than 30 API. Of course, we need a separate recovery techniques to recover these 2 different types of oil. Then we look at the area number 3, which is in the Swift current zone, that most of the oils are in the middle Jurassic Estevan carbonate, which is close to 20 API, so between at the middle of the heavy oil and the medium oil. Then we also have some Mississippian Bakken oil and some Viking oils. Once we come to the area 4 in the southeast Saskatchewan, we have lots of production horizons, more than 10. And of course, the majority of the oil productions happened at the Mississippian age carbonate oil. So let's come to a little bit detailed breakdown of each zones. So in this area number 1, Lloydminster, you can see most of the oils are from the Mannville group. We got 17 oil reservoirs or 17 oil pools that are larger than the 40 million cubic meters OIP. They're sufficiently big. However, when you look at the remaining OIP, the majority of them are higher than 90% or 80%, which means there's still a huge potential for either the enhanced oil recovery or other oil recovery technologies, including CO2 injection. Coming to area number 2, Kindersley Kerrobert, we have 7 giant oil reservoirs with OIP larger than 7 million cubic meters. Still, most of the oil pools still have a lot of oil left behind. Majority of them are more than 75% of our remaining OIP. Swift current, many oil pools are small enough, so you can see majority of them are less than 2 million cubic meters. And while we still have 7 large ones, while for the residual oil saturation or the remaining oil in place, they are recovered to a larger extent than other oil pools in the province. Well, coming to that area for Weyburn Estevan area, we can see that there are 260 oil pools in this area with more than 10 production zones. And there are 8 giant oil reservoirs in the orders of OIP. They are Wheelfield, Weyburn, Stillman, Midale, and Frobisher, Midale, Torquay, Tataqua, Pinto, and Stillman. So you can see that there are huge potential of enhanced oil recovery, including CO2 EOR. And of course, we have known that for a long time, Weyburn and Midale CO2 flooding has been implemented for more than 2 decades in this zone. So interesting plot is if we draw a circle with 100 kilometers radius at the center of boundary, then we can see that this circle covers a large amount of oil pools in that area, which means with manageable cost for CO2 pipeline construction and transportation, we will be able to target a lot of oil pools in that area. So Saskatchewan has been the flagship of a CO2 EOR and storage project in Canada or even the whole world for a long time, mainly because several world-renowned project, CO2 EOR project, and Saline Aquifer storage project. I will not give details of these several projects here because our colleagues and PTRC colleagues will give a lot of more information in these several projects, but I will just give a quick overview of this. So Weyburn CO2 EOR has been implemented since 2000, over 2 decades for now. And if you can see, huge enhanced oil recovery are caused by CO2 flooding. And Whitecap, as the current producers right now, is still considering expanding the CO2 EOR project to the newer zones, which means that the CO2 will still cause the increased oil reserve over the years. Just a quick reminder that we, as the Saskatchewan Research Council, has been doing this CO2 EOR project for the Weyburn feasibility study ever since the mid-80s. So by that time, nobody was really aware that just such a huge success of CO2 EOR in the Weyburn or in Southeast Saskatchewan. So we basically started a lot of laboratory evaluation or feasibility studies back then. Aquifers project is not a flagship that PTRC has led for years. So I'm not giving details here either, but here you can see that the Aquifers project is targeting at the Deadwood Formation, which is about 3.4 kilometers down deep, way above the basement in Southeast Saskatchewan. As a petroleum lab, reservoir engineering design is a very important step to evaluate any CO2 EOR or storage project before it goes to the field implementations. So the first step is always to collect lots of data, the production data, the fluid data, and the rock data, so that we can have important information for the input for the future numerical simulation or field surveillance modeling. Then comprehensive laboratory analysis will be conducted to find important properties for the targeted oil reservoirs or saline aquifer formations. That includes all the properties for the fluid, for the reservoir rocks, and also the interactions between the reservoir fluid, rocks, and the injected CO2. Then the next step will be the numerical simulation in different aspects, including the PVT, EOS modeling, geochemical modeling, geomechanical modeling. All this modeling will provide the results using the input from the laboratory results and provide the predictions for the field scale operations. Finally, when the project goes to the field, we will provide the field surveillance and monitoring using different types of tools for the field operations. So talking about the SRC experience on CO2 EOR, it dated back to mid-80s. Back then, as we said, we didn't really know whether CO2 flooding has a future, basically, in Southeast Saskatchewan or in the Central West Saskatchewan. Then we organized 3 big R&D consortiums back then, and that's basically a consortium of a group of oil companies working in the area. Then we have conducted all types of laboratory tests to evaluate the properties such as minimal miscibility pressure, PVT properties, or the oil recovery performance through Coreflood. Then we'll provide the important engineering design data for the coming CO2 EOR project in the field. And if you look at the literatures back then, you can see a lot of Weyburn, particularly research papers, were generated from our lab. Most specifically for the Weyburn IEA GHG CO2 monitoring and storage project, we have been involved since the very beginning. So we collected fluid, we measured a number of important properties, including minimum miscibility pressure, PVT properties, Coreflood recovery performance, and also once the commercial CO2 injection has implemented in the field, after several years, we went to the field to collect those fluid and monitor the fluid behavior changes between the injected CO2 and the reservoir oil. So here is some very old video that we took using the cassette tape back then. So that's probably more than 20, 25 or 30 years ago. And that's a real Weyburn live oil with CO2 RBA test imaging. And that's probably the only one around right now. So we can see that more pressure showing the original video. I'm just taking two at or above MMP to show you how the CO2 Weyburn live oil behaves. Now, when we go to the newest Bakken CO2 flooding design, we did exactly the same thing, except using much more advanced cameras to take the videos. So we can see that at immiscible flooding conditions, CO2 bubbles remains and rise all the way to the top of the RBA tube. When it's near miscible, we can see the CO2 bubbles will quickly dissolve and disappear. By the time it's at miscible conditions, CO2 will dissolve right away into the live oil, Bakken live oil. And you can see that there's huge difference in the color and of course in the density and the viscosity of Weyburn oil and Bakken oil. But you may wonder why the miscibility for these two oils are close. And that is because the Bakken oil has a lot higher GOR, or in other words, dissolved the gas than the Weyburn oil. So that it causes a lot higher minimum miscibility pressure. So as we mentioned before that, when you study CO2 injection into either depleted oil, gas reservoir, or geological formations such as the saline aquifers, the most important property is not only the fluid itself, but also the interactions between the fluid and the reservoir rock. So that's why we focus so much or emphasize so much on the interactions between the injection CO2 with the formation rock, oil, and brines. We all know that whenever CO2 is injected into the saline aquifer or formation brine, you will introduce lots of complicated geochemical reactions. Such reactions will either dissolve the rocks so that you can have higher porosity and permeability, or in a bad way that you will dissolve the cement, which is carbonate, then release the big grains like feldspar or quartz, so that this big quartz may plug the reservoirs. So really it's a case-by-case study that for a particular zones that you want to inject CO2, you want to look at complicated geochemical reactions between the CO2 and the formations, fluid and the rocks. Asphaltum precipitation, always an issue when you inject CO2 at high enough pressure to meeting oil like Weyburn or hair oil in Lloydminster. So Weyburn, we know that it meeting oil 28 to 32 API, that you can have asphaltum content all the way from say 5 to 6.5 weight percent. And we have done this research probably back 30 years ago to quantify how much asphaltum has precipitated at different CO2 concentrations. The CT scan image of the Coreflood results will also realize that how and where the asphaltum deposition occurs in the Coreflood. The biggest recovery mechanism for CO2 injection into any oil is viscosity reduction. So here we list the three different oils: the Weyburn meeting oil, Bakken light oil, and Lloydminster heavy oil. You can see that as the saturation pressure increase or the CO2 concentration increase, you cause significant viscosity reduction for the reservoir live oils. Coreflood result also showed a great recovery performance for CO2 flooding. Of course, we need to differentiate when we look at the recovery performance between different field or different oils. We need to differentiate the injection pressure and the injection rate, also the injection pattern, which is either continuous CO2 injection or WAC, water alternating CO2 injection, or how many cycles of a WAC. So all this will cause the difference between the EOR performance itself. However, we still can put these three images together to see there are difference in a nutshell. So for Weyburn medium oil, the CO2 EOR at this particular Coreflood is 17%, which is the summation of CO2 injection and the extended water flood. When it comes to the Balkan live oil, CO2 miscible flooding can recover extra 43% of reservoir oil, OIP. And of course, you need to pay attention that how much CO2 has been injected into the core. For the Lloydminster hair oil, the biggest adverse mobility ratio is an issue, so that you want to inject CO2 in a WAC format or in another different format, so that you won't cause big CO2 bypass issues. Still, you can see that with the full WACs of CO2 injection, there's 23% of enhanced oil recovery for this particular Coreflood. The injection pressure at this Coreflood is 5 MPa. For the numerical simulation side, we can do geochemical modeling, we can do the geochemistry modeling, and we can, of course, do the history matching of Coreflood and the equation of state modeling. So for this particular geochemical reactions of CO2 injection into saline aquifer, we identify that whenever CO2 is injected into this aquifer, you can see the increase of quartz, carbonate, anhydride, and of course the dissolution of calcite, dolomite, feldspar. Of course, some clays will be formed through this CO2 injection. So that we need to look at the possible permeability and porosity increase or decrease. Really depends on the injection conditions and also the ratios or percentages of each minerals in place, and also, of course, the saline brine compositions. For the CO2 EOR or storage for the Lloydminster hair oil, over the years we have done many different type of injections or EOR methods. So take something for example, there are steam plus flue gas injection. These are some pilot projects that going on in the fields, and we send our truck to the field to take the fluid samples, and we do the laboratory numerical simulation to help the oil producer optimize the injection strategy. Also, we have conducted lot of field scale, the laboratory scale injection tests, either flood or the WAC or the cyclic solvent injection using CO2 or mixture of CO2 with other hydrocarbon solvent. And we have different physical models in the lab, all the way from regular 12-inch or 6-inch long to big ones like this 2-meter long 3D physical model. So that is comparable to the actual size of the pain zone in the Lloydminster heavy oil reservoirs. So in a short summary, that Saskatchewan is a great place, probably one of the best in the whole world for testing the CO2 the whole flow string of CO2 capture, injection to either depleted oil or gas reservoirs or saline aquifers. So we have all the needed component to study all these whole mechanisms, all the way from the capture to storage. Of course, before we can implement the field operations, a well-designed laboratory evaluation will be required to generate lots of engineering designing data. Understanding important behaviors between the injected CO2 with formation rock and fluids will definitely help the design of CO2 injection process, so that we need to have more the first-hand or the real measured experimental data instead of predictions from correlations or mathematical models. So basically, the laboratory data will be used to tune or to model the complicated or large-scale process of CO2 injection for the real field cases. Thank you for your attention.